So the Compton Effect was discovered by Arthur Compton, and he received a Nobel Prize for it in 1927, and he also discovered the phenomenon of the total reflection of X-rays in 1923. So he had a few other achievements in his career, including working on the Manhattan Project. And he completed work on the interaction of Earth's magnetic field with the incoming isotropic stream of primary charged particles. So that's basically what effect the Earth's magnetic field has on charged particles hitting the field.
All right, so on to what was happening in our experiment. So what we had, cesium-137 was our source of, which is our radioactive material. So what it's doing, it undergoes beta minus decay so that it becomes more stable. And when that happens, it creates barium-137, an electron, and a neutrino. And then barium is also unstable, so what it does is releases a gamma ray. And so that's what we were measuring. We were measuring the energy of the gamma rays that barium-137 was emitting. And you can see here, this is it like splitting out into the electron, proton, and the neutrino. And here's another chart of it coming down, dropping an energy level to become more stable.
So this was our setup. So you can see here our cesium-137 source, the metal ring, which was made of copper. This is called a shadow bar. It's just a block of brass that is intended to keep the radiation from the source from going directly to the detector, because what we're trying to measure is the deflection off of the ring. So this is the path that the rays are taking. So it leaves the source here and then deflects off of the metal ring, and then that travels down into the detector, and then all of the radiation that goes straight from the source to the detector is being blocked by the shadow bar.
All right, so here we had to solve for basically what the distance was from the source to the detector. So you see just a triangle, but the detector is over here, as you can see on the slide before. So yeah, it's going from the detectors on this end. The ring is the top of the triangle, and then this side of the triangle is the source. So source, the side of the ring, and the detector. And this is actually the middle of the ring, so this R is radius. So we were given a bunch of values for theta, which is the angle, this angle right here. And so the particles are coming off here, hitting off the ring and going into the detector. So we were given values for this, and we had to find the distance from the source to the detector. That was one of the steps that we had to do. So we used trigonometry. If you remember SOHCAHTOA, that's what we used. So just to walk through how we found it. We found the supplement of theta, which is just a plus b. And then we knew what S1 was, so we did. And we also knew what R was, so the tangent of S1 over R. So we found that, we found what A was, and then we knew this, and we find B. So we found B, 180 minus theta, and A. And then we found B, and the tangent of B is X over R, and we knew what R was, we knew what B was. So we could find X, and S1 plus X is the full distance. So yeah. And this is just, this is another way of saying what I just explained. So seated here really helps with putting what I did with SOHOTOA into an equation that we could then plug into Excel to make our lives a whole lot easier. And here's the graph that it spit out for us. The data, yep, not the graph. So yeah, so you see the angles in degrees that we were given, and then instead of having to calculate all of these, we plugged them in and we got all these values. This is the distance from the source of the ring. Yeah.
And as you may have guessed, we also use the JINA data collection software. And in order to find just the energy value of the gamma rays scattered off the ring, we had to do two tests. One, first just a background run with no ring, just the gamma rays. And then we had to do a run with the ring and the background. So we could strip that graph, this graph from that graph to get this graph with just the peak of energy that we want. And then this is our third run and our seventh run. And you can see as the angle gets larger, the peak shifts to the left, which means the amount of energy is getting lower.
Okay, so this is our second set of data. The FWHM is full width half maximum, which is if you take a bell curve or a Wheeling like Gaussian curve, and you could go halfway up the height of the curve, the distance between the 2 points on the bell curve is the full width half maximum. And the integral, which is the number of counts, so the number of gamma rays that the detector actually picked up, and those may seem arbitrary, but they're used to calculate using sigma to calculate the standard deviation, which is our error. And the energy levels there are what she was talking about going down. This fancy equation here is the Klein-Machina formula, which predicts the differential cross-section of the scattered photons, which just means that it's the rate at which the scattered photons at a particular angle are, and given in both those locations, are detected. And you'll notice here that the mass of electron is given because the gamma ray emitted from the source actually hits electrons in the copper ring. So this is our graph. So we plotted the values that we calculated from the Klein-Machina equation against our actual data. And as you can see, it conforms almost perfectly with the data. And we have the angle versus the energy. So as you can see, as the angle increases along the x-axis, the energy decreases along the y-axis. Okay, so this is our standard deviation, and that's just our error. And as you can see, relative to the 600s where the energies was recorded, it was only around 1/2 to 1.5, which is exceptionally small. And as you can also see that the error is going up over time, which can be accounted for that less radiation is being bounced off the ring, so the background radiation composes a larger percentage of the R readings. And then that's just as a percentage, and it's really, really small.
So why should you care about the Compton effect? Essentially, it's important to know that the energy was changing as the angle got smaller, but the intensity of the gamma rays didn't change. And when particles are scattered at various angles, their energy is going to change, but not their intensity. But when waves are scattered at various angles, the intensity will change, but not the energy. So this was the first time historically that experimentally it could be determined that light acts as a particle. They already knew it was a wave, but here we knew specifically the dual nature of light. And that is why this is important to science.